a satellite image or like even like a land use map doesn't create impact, right? You need an application that changes behavior.
Welcome to another episode of the Mapscaping Podcast. My name is Daniel, and this is a podcast for the geospatial community. My guest on the show today is Rob Emanuel. He is a geospatial architect working at Microsoft, and he's building something called the Planetary Computer, and that's what we're going to be talking about today. Just a quick heads up before we dive into the episode. Rob mentions this idea of blob storage quite a bit during the episode, and I thought it'd be handy if we were all on the same page. So blob is short for binary large object. And some of the typical examples when people talk about blob data, they talk about images, they talk about audio files, they talk about multimedia. So during the conversation, when Rob talks about blob storage, he's talking about storage of these binary large objects. So blob storage is simply an optimized way for storing massive amounts of these kinds of unstructured data. Hi Rob, welcome to the podcast. I believe you're the first geospatial architect that I've talked to on the podcast, so I would really like to hear about that, how you got involved in geospatial, how you ended up as a geospatial architect, and of course, I'd really like to move on and talk about the planetary computer that you're building at Microsoft. But let's start with the geospatial architecture first.
Yeah, absolutely. Thanks for having me on. I am a geospatial architect at Microsoft. What that means is that I'm architecting systems on Azure and the cloud, dealing with geospatial data and analytics. So my expertise is in geospatial software development. I've been a software developer for, I can't even remember how long. But I got into geospatial first through a company called Xavia, which is the company that I was working to previous to Microsoft, where we did large-scale raster data processing through a project called GeoTrellis and some deep learning for satellite and aerial imagery through a project called Raster Vision. I was the VP of Research and Development there until about a year ago when I started on the team that's working on the Planetary Computer at Microsoft.
Just out of curiosity, is it a big jump to go from being a developer to being an architect?
No, I do a lot of software engineering, but also sort of designing systems. It's pretty much the same thing. It's just a fun title, really, for an engineer who's building geospatial. I'm happy to have the title that I have, but it's really similar to other people doing software engineering for geospatial.
Well, thank you very much for adding a bit of context to the conversation in terms of your background. But the main topic of the conversation today is the planetary computer. What is a planetary computer?
So the Planetary Computer is a modular set of components that is really aimed at enabling geospatial solutions and analytics in Azure, but sort of in general. We're really looking to use Microsoft's technologies and capabilities to accelerate the building out of applications and solutions that have an environmental impact. And so a lot of areas of environmental sustainability need geospatial data, and geospatial data is incredibly large. We're talking about not just imagery, but for instance, like climate model projection data, you sort of need the power of a cloud to do that type of processing, unless you have a supercomputer, which most people don't. So we're building out components so that we can host that data, make it available to anyone, also be able to search that data and make it more useful. If you have a pile of files in blob storage, that's great. But if you're only interested in a specific time and a specific location, you need effective ways to find the data that you want. And so a large component of the Planetary Computer is the APIs for doing spatiotemporal searching of that data. And then once you have the data that you need to do analysis to it often. So we provide a Jupyter Hub environment that runs next to the data in the cloud so that people can use their favorite open source and our favorite open source tools to do the sort of earth data science work for analyzing that data. And we do it, the Planetary Computer is really designed in a modular way so that people building production solutions can take whatever components make sense for their architecture and build it into their applications, because we want to really aim these capabilities at people who are making, solutions that are used for impact.
I want to try and summarize this a little bit here. It sounds like you're hosting data, a huge amount of data, environmental data, it sounded like. So this is part of these modules, or these components that you talked about. So we've got the hosting component, we've got the search component, and we've also got a compute component. Am I on the right track?
Yes.
Wonderful. I would really like to start with the hosting of the data first. Could you give us a little bit more information about that? What kind of data sets are you hosting?
So there's a lot of publicly licensed satellite imagery, similar to other cloud platforms. We have the Sentinel datasets, Landsat. We're really excited to get Landsat 9 into the Planetary Computer once the images start becoming available, but also things like elevation data, the point cloud data that can be used to derive various elevation products. We have climate model projection data. We have biodiversity data, derived products from remote sensing, things like Sentinel-1, 3, and 5. Just a large range of publicly, openly licensed data sets that can be used in geospatial analytics.
So some of those are incredibly big data sets. If I'm understanding this correctly, you're taking a copy of those existing data sets and moving them into your environment. Is that correct?
Yeah, that's correct.
Okay, and you named quite a few different sort of data sets that are derived from satellite platforms. Are we just talking about raster data here?
We're focused primarily on raster data for the APIs that we're developing, or at least that's the majority of the use cases is cloud optimized geotiffs stored in a Stack API. However, there's different formats that we're hosting. So we're currently hosting NetCDFs, we're ZAR datasets, also some vector datasets, some Parquet tabular data that contains geospatial features, but in a Parquet table. So there's a real wide range of the data sets that we are targeting to host. And I also mentioned point cloud data. I think raster data with the cloud optimized geotiff format is the sort of most accessible to this type of system currently. And I think a lot of like other data formats are learning a lot about how people are using raster data. Also, that's my background. I think the other sort of like large component is the sort of ZAR, NetCDF, climatology data sets, doing a lot of work on the cloud. And so as these formats sort of advance and become more cloud optimized, we're exposing more and more different types of data.
I just want to clarify, when we talk about cloud optimized, are we talking about streamable data?
Yeah, streamable data where you can host the files in blob storage, and there's a way to get only the bytes that you want. If you're dealing with large sets of data, often they're like large files or many small files. There needs to be a way to only read the bytes that you want, or else you have to download the entire, set of data into your local machine, which oftentimes is not even feasible depending on the size of your machine. So when it's cloud optimized, it means that it's optimized for reading windows or pieces of that data set that is hosted on the cloud, and you're not really reading anything you don't need to.
When we talk about reading, so I think for cloud optimized geotiffs, for example, we're talking about reading a spatial extent. Like I'm only interested in this piece of data. What about reading and streaming temporal data?
So that's where, ZAR or like there's a lot of work going on with cloud optimized NetCDF, which really uses ZAR metadata to index into NetCDF files. But it's a similar thing, right? There's a spatial dimension. There's two spatial dimensions in a raster in the sort of gridded n dimensional format that is, what NetCDF or ZAR encapsulates. You're just adding the spatial dimension to. So you're saying this area, this time, find me the set of bytes, and they can be like centrally located or located in a number of files. Just find me those bytes and then read those. So it's really an index into an n-dimensional array of data.
But when you're moving these large data sets over from wherever it is they're being stored, hosted today, and bringing them into your environment, I'm assuming you have to convert them into these cloud optimized formats. How do you decide which format to use? Like, what does the decision look like when you're looking at a data set? Okay, should I store this as a cloud optimized geotiff or as a ZAR? What does your decision process look like? And do you even have to make that decision, or do you just store them as both?
Yeah, that decision process has been interesting in some cases. Sometimes it's really easy. I mean, Landsat comes in cloud optimized geotiffs already, and things that are like really a snapshot of time that is not temporally dense, right? Like a satellite imagery, an individual capture that has a really well-defined footprint on the Earth is just good for raster data. So cloud-optimized geotiffs is an easy answer there. However, there's some formats that are stored as non-raster formats, right? And like HDF and NetCDF like can store raster data inside them, oftentimes do. For instance, the GOES 16 and 17 satellites, the data that NOAA offers is through NetCDF files. And actually, the projection information encoded in those NetCDF files is pretty tricky because the satellite is so far back, it's taking such a wide picture of the Earth that the actual like footprint of the Earth, quote unquote, can go outside of the circle of the view of the Earth. So encoding that, so when we were processing that data, we're storing the original NetCDF because we want to make sure not to make too many editorial or we don't want to make too many modifications on the scientific data that people have been experts in and are offering, right? We want to offer as close to the original data set as possible, but then we exported cloud optimized geotiffs for each of the bands in the CMI, the cloud and moisture imagery product of GOES. And it turns out that those rasters, some of the open source tooling dealing with rasters can't handle the projection information as well as you'd like. And actually that affected our ability to visualize that data. So we also offer a Web Mercator reprojected version of the first three bands, which are used for visualization, just so that you can explore it using our tool to put the images on the map and be able to find the images, actually see the images that you want to use. But when we're making decisions about data sets that are not so clearly obvious to use raster data for, there's a discussion in the community about what is ZAR good for versus cloud optimized geotiffs versus some other formats. So our take on that so far, basically we have conversations with community members, with the data providers to try to figure this out. And so what we've kind of come across so far is that if you have temporally dense data that you want to actually chunk, you want the individual components of the file to be accessed in chunks of time, then that's where something like a cloud optimized NetCDF or a ZAR format would be better. But we do have to make that choice, and we're continually thinking, okay, should we host this in cloud optimized geotiffs? Should we host this in another format like ZAR? Is this more of a point cloud data set? Should we host multiple chunkings of each of the data sets? So yeah, it'll be interesting to see how the cloud optimized formats of these data transform, and based on user input, if we end up actually hosting multiple copies or transforming the data to make it more easily accessible.
So I think you've done an absolutely brilliant job of describing the hosting decisions you're making for each data set. Could you talk to us about how you make these data sets searchable, how you expose them to the world?
Sure. We lean really heavily on the amazing work that's going on in the Stack ecosystem, the spatiotemporal asset catalog ecosystem, which is an effort that arose from a number of people who were building out APIs to do this type of work, to make geospatial data available on the web and searchable. And organizations were kind of inventing their own sort of metadata standards or just figuring out for themselves, okay, how do we encode these similar properties of Earth observation data and other spatiotemporal type data, where a bunch of us met in Denver for the initial Stack sprint before it was even called Stack, and put our heads together to think about what does a implementation driven standard look like that is flexible enough that it's not going to take a long period of trying to nail down a specification that covers every single use case, but instead is something that we can iterate on through GitHub and not be super strict, be extendable, and be implementation driven. And so Stack came out of that, and I believe it's picked up a lot of steam, and people realize that it's a way to just encode metadata for spatiotemporal data, whether it be rasters or point cloud or anything, and have a common language, a common JSON schema to be able to specify, what does this data contain? How much information can I contain about this data? And what that allows, an API to do is then build a database that indexes the metadata for its spatial component, its temporal component, and allow searches over that data, and then have a very well specified return value. So applications, whether they're building against the Planetary Computer Stack API or they're building against the Element 84 Earth Search API, they're getting the same sort of information in a standard way.
Could we draw any comparison at all between Stack and perhaps the GET capabilities request of a web feature service?
Yes, actually. So WFS is being superseded by a standard called OGC API features. And this is part of OGC's new suite of standards under the sort of OGC API umbrella. And so Stack itself is comprised of two different components. There's Stack Core, which is the data models, and then Stack API, which itself is an extension of OGC API features. So they're really not one and the same, but Stack API is a version of OGC API features. It reuses all of the sort of language about collections and items and all of the API specification of how you do searches, the way you specify the query language in the CQL2 language now. So, and the Stack community has been working closely with the OGC API features community to sort of get the standard working in both cases. But yeah, I would consider the Stack API as a specific application of OGC API features.
We've talked about the hosting of data, and now we've talked about how you're exposing this data to the world, how you're making it searchable, how you're helping people find the data that you're hosting. Can you talk a little bit about the Jupyter Hub that you're hosting?
Yep. So, in order for the data to be most easily accessible, give the fastest access, and also, with cloud providers, often if you're moving data across data centers, there's an egress fee that somebody has to pay. So you really want to move your compute next to the data so that it lives in the same data center as the data. And so, there's plenty of ways to do that. The Pangeo ecosystem has like a rich set of documented ways to deploy Jupyter hubs with open source tools so that you can do earth science analysis, data science in cloud environments or on supercomputers, HPC systems. But you have to know how to like deploy that, and it's a pain to manage a deployment of a Kubernetes cluster that lives next to the data. So we provide a service that we're doing the management of the deployment of that system and the maintenance of the images that contain all of the most up-to-date open source libraries, and allow users to request access to that Jupyter hub in which they get an account and they can sign in and use a pod in our Azure Kubernetes cluster that lives in the same data center right next to the data.
So you're talking about I need to apply for an account there. Are there certain pieces of this that are pay to play and certain pieces of this that are free to use?
Everything is free to use. The data and APIs are anonymously accessible, right? You don't have to have an account to access them. You can just go to the public endpoint. There is a token mechanism that you have to use in order to access the data, which is just a way for us to control egress, but it's also anonymously accessible. You just hit an endpoint, you get a token, you can use that token for a set expiration date, and then you just can get another token. And it's a bit rate limited, but it should be enough for doing large scale jobs.
So just so I understand this, let's say I search the stack, I use the endpoints that you're exposing to the world. I search through the data you're hosting. I find something I'm interested in. What do I get back? Do I get back a URL that I can pull that into my own system and then start streaming data from your hosted blob store over to whatever it is I'm doing for free?
Yes. Yeah. So you get it with the stack assets, you get an href, which is a URL. And then so that URL won't work on its own. You just have to hand that URL to a second API and say, hey, sign this. Or you can request a token and sign it yourself, but it's just appending a query parameter to the URL. And so if you found the data you wanted, you have the stack items, you have all of the metadata to say, okay, this is the data that I want to work with. And now there's a variety of open source tools to integrate to turn stack items into, data, either X-arrays or VRTs now with the new release of GDAL. But you would have to sign those URLs prior to accessing the data. So it's just one little step in between.
So by signing a URL, are you talking about getting a token?
Yeah, getting a token. Yep.
So this sounds absolutely amazing. So this means that I could be sitting at home here and I could search your catalog, find some data I'm interested in, pull it into QGIS, for example, and start working on it for free. Incredible. Why is Microsoft doing this? Why is Microsoft providing this service? What's the sort of motivation for Microsoft to do this?
So Microsoft has taken a stance that in order for Microsoft as a business to do well in the long term, the world needs to do well. And there's something in the way of the world doing well if you take, a decade's outlook, that is climate change. So Microsoft has, dedicated large investments to teams of people working on ways to utilize the vast resources we have, the cloud that we have, the technology that we have, and say, how can we make an impact on this? Because it is actually in our long-term business interest to move the needle on climate change. And so as part of that, in 2020, there was some announcements made around commitments that Microsoft was making around carbon, water, waste, and ecosystems. Carbon by 2030 will be carbon negative, and by 2050, we'll have removed all of the carbon that we've ever emitted as a company since the founding. The commitment to be zero waste by 2030, to be water positive, to replenish more water than we use by 2030, and for ecosystems to, by 2025, protect more land than we use, and to also build a planetary computer that enables environmental sustainability solutions through the use of data in the cloud.
Wow. I mean, this sounds absolutely amazing. It really does. There's another company, a little company out there doing something similar, and it's called Google. They've got something called the Google Earth Engine. You might have heard of this.
I have.
Yeah, and right at the start, you said that you were a geospatial architect. I'm wondering when you thought about building these things, when you were hired to build this by Microsoft, did you look at what Google was doing and said, okay, that has been done, so we need to do something different? Or is this just the best architecture to solve this problem, to help to give people access to the data?
Well, first off, Google Earth Engine is doing amazing things and has been around for a long time and is a great platform. And so, certainly, when I was hired, I looked at Google Earth Engine among other platforms that are doing this type of, enabling geospatial analytics. And, one thing is that there's plenty of people who use Google's cloud platform and want to integrate with the data sets that Google Earth Engine has to offer. Microsoft has a vast number of users and companies using Azure. And so to enable their geospatial workflows, we also have to host the data. AWS is doing it too. It's becoming sort of baseline to be able to offer those data sets in a way that doesn't mean you're pulling things off of FTP servers or across clouds. The different approach that we ended up taking is more around building out that modular set of components that really focuses in on the open source ecosystem. I've been contributing to and a big proponent of the open source geospatial ecosystem for many, many years. And I believe it's such a valuable asset, not just in the fight for climate change, but just in general, like what's available in the open source ecosystem for dealing with geospatial data is so valuable to so many people and so many companies that anything that we're building should try to take advantage of that as much as possible and contribute back to that as much as possible. So we want to be in a situation where if people want to use the best in class open source that was just released 6 months ago, and they want to build a PyTorch model against this data, and they want to pull in all of their neat Pangeo ecosystem tools, we want to enable that. And not just enable it, we want to be on the front lines of, okay, what do these tools need? What do these projects need? How do we support them? And how do we contribute to them? So really it's a method of, it's just an architecture of bringing in that open source ecosystem. So that a little bit draws a distinction between us and some other platforms, including Google Earth Engine, which is so super powerful, super feature rich, and amazing. People are doing amazing science on it. And, we're friendly with the team. They contribute to the Stack ecosystem. There's Stack collections for each of their collections as well, right? We're looking on we're playing in the open source ecosystem as, collaborators, even if our companies are competitive. But yeah, that's sort of the difference of approach that I'd say we're taking.
Yeah, I really appreciate you walking us through that. And just out of curiosity, you mentioned you looked at so Google Earth Engine among other platforms. What other platforms did you look at in terms of getting inspiration for building the planetary computer?
So there's a number of platforms. I mean, Descartes Labs is a great platform that really, enables this type of analytics and very fast access to the data that's hosted on the cloud. Synergize also has a really great, setup with Sentinel Hub, Esri with, their image server and notebook-based workflows is, sort of similar solutions that we definitely took a look at and want to integrate with as much as possible, which is part of the reason we're choosing to move forward with Stack, because even though we're sort of using our own deployments of open source tooling to expose the data and the functionality, if we're all just using the same standard, or moving towards using the same standard, then these things become interoperable. And if somebody's on a Descartes Labs notebook and they want to pull in some planetary computer data, great. That's that we want to be able to enable those types of situations.
So obviously, there's a lot more platforms out there than I was aware of. When you think about some of the key technologies which are making these platforms, these kinds of things possible, are we just still thinking about cloud computing, or are we thinking about streamable data or formats like the cloud optimized GeoTIFF? Are we talking about the stack, or is there's something else? If you had to sort of point your finger at some of the key technologies which are making these platforms possible, what would those be?
Yeah, I would say the, blob storage is really not only what's like making it possible, but sort of filling the need. If you're working with this type of data at this scale, either you have an amazing machine that you own or you're working in the cloud, right? And so there's the cloud itself with its very, it's a planetary computer, right? And a computer has storage and it has compute and it has some GPUs amongst many other small parts. But if you think about it in that framing, the ability to have cheap object storage that can hold petabytes and petabytes of information that anybody can access from VMs, whether they be running in a Kubernetes cluster or like, Azure Batch, which we use for our large scale processing. There's compute available to take advantage of that data, right? That's and then GPUs to do your, machine learning training and inference. Those are the sort of core components of a cloud platform, the very primitive, basics that you need to do this type of analytics, data processing. And so because of the need to scale, 2 petabytes of data, that's where, these cloud platforms are sort of, a necessity. And there was a recent paper around users of big Earth data that did a survey of users, and most users are still downloading data, which makes sense, right? You talked about pulling some data files, loading it up in QGIS. That's, I still do that when I want to like, look at certain images, right? But if we're going to enable the type of geospatial analysis that we need to do at a global scale, it's going to have to move into the cloud. So yeah, these platforms are really trying to take advantage of the compute and the storage available and put it into the hands of users who are traditionally bound to desktop systems that have limited capabilities.
So obviously, this is an incredibly complex and difficult puzzle to solve. It cannot be easy deciding which data sources to host, how to host them, how to provide access to them, and then obviously all the considerations around the compute. What tools do we make available? All of that kind of thing, and doing this at a massive scale. This can't be an easy problem to solve. But what's the hardest bit about building this? Do you think? Like, if I could snap my fingers and solve one problem for you right here, right now, what would that problem be?
It's a good question. It's a good question. I think it's, right now we're pretty hyper focused on capabilities, which start with the data. So enabling data sets that are openly licensed to get into storage and not just data sets that are in our purview, but allowing anybody to be able to push data into this system and index it in a way that really, really richly describes the data so that you never have to look at any data that you don't want to, right? So getting the stack standard and all of its extensions completely filled out so that it describes perfectly, in an idealized world, describes perfectly the data that it represents, having that implemented across not just the Azure Planetary Computer, the Microsoft Planetary Computer, but every system that is hosting geospatial data so that everything is interoperable, and then enriching that metadata through the machine learning that we all know is going to be necessary in order to sort through all of this vast amount of data. And then I think the last thing, if you could snap your fingers, is really solving the sort of data fusion problem of, how do we make it so that we don't care if it's a Landsat or Sentinel scene. Actually, everything is sort of normalized into this description of some area of space and time that we can kind of use together as one set of descriptions, no matter what sensor it came from, in order to fuel analysis, and then making it super easy for users to build applications where even if they're not geospatial developers, they don't know what a CRS is. How do we sort of abstract all of that away so that you're only getting the information that you're interested in about a location, and that fuels your solution or your science?
Right at the start of this conversation, you mentioned about this interaction you have with the community. You're saying you're asking the community, what do they want? What do they need? How can we make this better? What's working for you? And I think you were referring to, at that time anyway, file formats. How can we deliver this data to you in the best possible format? This is my next question. How do you know that people are going to use this? Are people telling you, hey, we want this? Or are you looking out in the market and saying, other people are doing it, we're going to do it too, there must be a need? And I guess what I'm sort of in a very roundabout way trying to ask is this a build it and they will come, or is the market telling you, hey, we need this thing here, we want this, and we want it to look like this?
I think there's a little bit of both, to be honest with you. There's a little bit of build it and they will come where, we're having the experience of what large scale geospatial analytics takes. And there's some baseline capability that is, sort of like, yes, let's snap our fingers and make that happen. However, one of the advantages of being at Microsoft is that we have a vast customer network of people who have real problems who are saying, hey, I need to look at geospatial data in this way. And solving those problems is, part of our purview, because I think that the planetary computer is aimed at environmental sustainability as its primary use case, but the type of horizontal functionality that's providing is applicable in many different use cases. And, somebody who's trying to, gain insights about a market based off of the changes in imagery has very similar capability needs as people who are trying to monitor land use change in order to understand how carbon is changing over those areas. So there's a range of information that we're taking in about what are the needs for geospatial analytics, and but we're also kind of looking ahead of the puck and saying, okay, we sort of know we know what's not possible right now that we need to make possible. So we're building that.
Okay, so staying with the theme of looking where the puck is going, what is this going to look like in 5 years' time, do you think?
I think it will look like the application of pre-existing machine learning models that are fine-tuned for your area of interest over a wide range of data, whether that's contributed by governments like NASA or data sets derived by users and scientific institutions, is going to be sort of very easy. It's going to be sort of, how do I actually apply these models for the solution that I'm aimed at, rather than let me go find those files. And really, you say 5 years time, and I'm laughing a little bit because if you asked me this 5 years ago, I'd probably say the same thing. So geospatial data, and especially the scientific sensors that are flying in space and collecting data, are so complex. I mean, synthetic aperture radar data is so complex. So yeah, all these different data types are it's taking a really long time to even get the basics down. So I hope in 5 years that vision is complete, and data is super accessible through a well-known format, completely described by metadata, and models are easily applied to that data to solve specific problems. And fingers crossed we can finally get there in 5 years.
Let's hope so. Hey, just the final question here. Earlier on, you talked about this idea of taking all that complexity and, abstracting it away for the users so they could just get on with the business of doing the job of, solving whatever problem they have. I wonder sometimes if we're not doing ourselves a bit of a disservice by doing that because we have almost unrealistic expectations, perhaps. You're talking about how difficult SAR data is to work with. You're talking about if you'd asked me this question 5 years ago, I would have said the same thing because it's a huge and difficult problem to solve, I guess. I wonder if we'd have more sort of realistic expectations, perhaps build something else if we, as a community, understood how difficult it is to do this.
Yeah, that's a fair point. And I think when I was saying abstracted away, I meant from a certain class of users, right? Or people building the things that are actually making an impact. Because a satellite image or like even like a land use map doesn't create impact, right? You need an application that changes behavior, that actually people who are making different decisions based off of. And so the decision makers that are using a solution, you don't want them, you want to hide the complexity of, all the incredible complexity of geospatial data and earth science. However, I think, a lot of your listeners and a lot of people that I are in my community are the type of people that need to take on that complexity and say, hey, we're the people that need to set those downstream users up for success by making it really straightforward, taking the complexity away and kind of shouldering that complexity through the tools that we build and through the information that we derive and how we present that information to users. So I think that there's a lot of work to do there. And currently, you sort of have to understand what land use change and how those things are derived in land use classes and even resolution of a map. You still need to kind of understand that to sort of take advantage of that information. And so it's like, how do we, as the geospatial open source community, figure out how to really do what we're best set up to do and take on that complexity?
Rob, I really want to thank you for your time. I really appreciate you taking the time to talk with me, to explain what it is that you're building, how you're building it, why you're building it, what it might look like in the future. Really enjoyed the conversation. Before I let you go, is there anywhere that listeners can go if they want to try things out? Can they apply to be part of some sort of beta testing, whatever? Can they get access to this? Can they reach out to you if they have any questions? Is there anywhere where we can send people that want to know more?
Sure, you can go to planetarycomputer.microsoft.com. There's a request access that you can request access to the hub. There's also documentation about our Stack APIs and the data sets that we have available. We have tools to be able to like explore the data on a map. We're also on GitHub, the Planetary Computer APIs, which actually build the software that we end up deploying for our APIs, is open source. The hub is open source. There's documentation about how you can deploy your own hub. There's also a GitHub repository where we're using GitHub discussions to have discussions about, what are people interested in? What are people's experiences? So please reach out to any of the team. Planetarycomputer@microsoft.com is also an email that you can reach out to us. We'd love to talk to you.
Thanks again for your time, Rob. Thanks for your patience. Really appreciate it.
Thank you. Really appreciate being on.
So I really hope you enjoyed that episode with Rob. I hope you enjoyed learning all about the Planetary Computer that Microsoft is building. And I hope you take advantage of this because it sounds really, really cool. So if you want to find out more about it, the URL that Rob mentioned towards the end there was planetarycomputer.microsoft.com. And I'm on that webpage at the moment and a whole bunch of data catalogs. There's applications, there's documentation. It's pretty amazing. So check it out if you're interested. If you've enjoyed this episode and haven't yet listened to the episode all about Google Earth Engine, I think you might enjoy that as well. Rob talked a little bit about Google Earth Engine during the episode, but to get a few more details about it, I'll put a link to that episode in the show notes of this podcast. And that's it for me. That's it for another episode of the Mapscaping podcast. Please feel free to reach out to me. You can find me on Twitter @Mapscaping, or there'll be a link to my LinkedIn profile in the show notes of this episode. Or you can simply email me, info@mapscaping.com. I would love to hear from you. Okay, we'll talk again next week. Bye.